So this video is a review for the most part of what you learned about the atomic model during first year, but we are going to add a little bit of new stuff. So make sure that you take some notes, follow the PowerPoint slides, read through the chapter on the atomic model so that you get some of the new ideas down. All right, so since we're talking about atomic models, let's make sure that you are comfortable with what models are. So what does make a good model? You've got model airplanes, you've got the atomic model, you've got models of buildings. What makes a model good? Well, you want it to be simple. You want it to explain what you can observe about it. So obviously a miniature is a good model because it lets you see everything that's involved. It lets you make new predictions, and it lets you test phenomenon. But you got to remember that models are not complete. They're not reality. They're just an example of what you're taking a look at. And that can be definitely emphasized with our conversation about the atomic model. We are going to keep it much simpler than what a real atom is. So the first atomic model was actually suggested by a man named Democritus. Hopefully you remember him. Long time ago, 400 BC. And what he proposed was basically the word atomus as the way of describing what matter is made of. They were small, solid, indivisible particles. And an example, you've got water here, you've got iron here. Notice that they are small particles, but they're not all the same shape. They interact with each other a little bit differently. Then we wait a long time, nearly 2,000 years, to take a look at Dalton's atomic model. A lot of his ideas still hold true today. He said that each element is made up of not atomos, but something called atoms. Atoms of a given element are identical. Atoms of different elements are different. Chemical compounds are formed when atoms of different elements combine with each other. And a given compound always has the same relative number of atoms. That leads us into two laws that Dalton is responsible for emphasizing. First one is the law of definite proportion, which basically says that if you have water, it is always going to be H2O. The law of multiple proportion says that you can have different ratios of the same element, making up different compounds. They wouldn't make up the same compound. For example, water is H2O, but if you take 2 hydrogens and 2 oxygens, you create something called hydrogen peroxide. Very different, even though both are made out of the same elements, the ratios are different, so you wind up with different properties. And then finally, he also said that chemical reactions involve the reorganization of atoms. And this led us into the law of conservation of matter, the fact that equations must be balanced to show that 20 atoms of hydrogen going in have to produce 20 atoms of hydrogen coming out, and so forth. All right, let's review a little bit more some of the history, talking about the atomic particles that exist inside the atom. Hopefully you remember all this stuff. If not, I'm guessing it'll come back to you pretty quickly. Rutherford is credited via his gold foil experiment with finding the proton and the nucleus and the fact that they are positively charged. You've got Thomson, who did a whole lot of experimentation with something called the cathode ray tube, and your textbook covers these ideas, and of course you can go online and learn about them in more detail. The AP exam doesn't focus a lot on this type of history, but sometimes names do come up. So Thomson is credited for identifying the electron. Millikan, who we don't really talk about a whole lot in first year, via his oil drop experiment was able to determine what the actual charge of an electron was. And then, of course, we still have the neutron, which was found by Chadwick doing nuclear bombardment experiments during the time when everybody was so into doing nuclear experimentation. All right, so let's review the basics. We're going to go through this pretty fast because I think you probably have had it enough to remember. Nucleus contains the protons and neutrons. That's what gives you the mass number. The nucleus is very small, but it's very dense because it has most of the mass, but very little space. Notice that the space is 10 to the negative 15 meters. That's pretty darn small. We consider it very dense. Since it contains the protons, it has an overall positive charge. The electron cloud obviously is where the electrons are found. Even though electrons have such a small mass, they don't really contribute much to the mass of an atom. They take up most of the space. So the electron cloud, notice there is 5 magnitudes of difference between the size of the nucleus and the size of the electron cloud. 10 to the 15 versus 10 to the negative 15 versus 10 to the negative 10. And the electron cloud, because electrons are negative, has a negative charge. Just some of the numbers. Again, if you needed to use one of these in a calculation, they would give them to you. You don't have to remember how many grams a proton weighs or what the charge of an electron is. You'll always be given those values as constants. But just remember that in terms of AMUs, protons and neutrons are essentially the same. Electrons are essentially 0. Notice that they are 1,000 times smaller than the proton or the neutron. And then charge +1, -1, and 0. Hopefully that's not hard to remember. All right, so next thing we need to review, isotopic notation. So you look at the symbol of an atom and you see the big symbol for the element in the middle, and then it's surrounded by as many as 3 different numbers. Do you remember what those numbers are? Let's see. A is representing the mass number. So that's how many protons and neutrons you have. So that's how heavy something is, one of the atoms. If you change the mass number, it means you've got a different isotope. So you could have 6 protons in a carbon atom, but you could have 6, 7, or 8 neutrons typically in a carbon atom. So that gives you a mass of 12, 13, or 14 for the different isotopes. Z, down at the bottom left-hand corner, is what we refer to as the atomic number. That, again, is telling you the number of protons. And so that's the way that we identify the element. That's the way the element is arranged on the periodic table according to atomic number or number of protons. And then finally, Q in the upper right-hand corner is the charge. So that's where we are comparing the number of protons to the number of electrons. If they are equal, we say that we have neutral atoms. But if they are not equal, you can have a cation, which has fewer electrons, so they are positively charged. Remember, you never change protons, you can only change electrons. So if we lose electrons, we've created a cation. If we gain electrons, we've created an anion with a negative charge. A little bit of practice, refreshing your memory of things. Obviously, you need a periodic table to figure this out. But if you know the number of protons, you can get what the element is. If you know the number of neutrons, you can get the mass. And with the charge, we can figure out how many electrons we have. With the charge being +3, that must mean we have 3 less electrons. So there better be only 30 electrons in there. So with an atom of 33 and a mass of 75, we have arsenic, I think. And then with a charge of +3 means we have, oops, not 33 electrons. We only have 30 electrons. Gonna have to change that. All right, if we go down and do the rest of them, 54 electrons gives us a -2 charge. You can see that, 52 protons, and then with 128 minus 52 should be 76. Hopefully I did that math right. Next element, if you have 16 protons, should be sulfur. 32 neutrons gives you a mass number, or I'm sorry, 16 neutrons gives you a mass number of 32, and then 32 electrons means you have a charge of 0, so we show nothing up here in the corner. Last but not least, 81 protons means you've got tellurium with 123 neutrons. Mass must be 204, and with a charge of +1, it must mean we have, I did the math right here, 80 electrons. All right, so table looks good except for this guy. This guy should be 30, not 33, so my bad. If you look on the periodic table, you remember, hopefully, you see what's not the mass number, but you see the atomic mass. So what's the difference? Mass number takes into account all the different isotopes. So it depends upon the isotope's mass as well as the isotope's abundance. So the atomic mass is really the sum of all of the products of those two things together. So next slide, we got an example. Lead has 4 stable isotopes, 204, 206, 207, 208. Those are the mass numbers, so those are protons plus neutrons. Their abundances respectively, you can see listed here. So how do we calculate the atomic mass? We are going to take 204 times, this is a percent, so we're going to turn it into a decimal form, so 0.014. Plus the 206 times the 0.241, and so on and so forth. You wind up with atomic mass of 207.241, which on every periodic table you typically see written as 207.2. All right, one other thing, and this is new, that we can do to help us investigate masses and so forth is do something called mass spectroscopy. It uses an instrument called a mass spectrometer in order to determine the mass of an element, or more often molecules. We can also use it to determine the various abundance of different isotopes of an element. And basically, we're going to do an activity on mass spectroscopy, but basically what's going to happen is the instrument ionizes the atoms or the molecules. So it turns it into +1 ions, and then it's able to be impacted by a magnetic field because it's charged. And that is the way that the instrument measures the different particles that are created. So here's a couple of examples. So let's say we've got this element and we run it through the mass spectrometer, and this is what comes out. We've got something with a mass of 70, something with a mass of 72, and something with a mass of 74. Notice that by far there's a lot more stuff of 70 and even 72 than of the 74. So this is relative abundance. This isn't percent abundance, this is relative abundance. So this is how much out of the whole you have. So to figure out the mass, you're going to do 9, the relative abundance, divided by the whole amount, which is 9 plus 6 plus 1 is 16, times the mass of that particle. So similar to what we did last time, except using relative abundance instead of percent abundance. So you wind up with these 3 numbers and a mass of 71. So we would say that this element is whatever element 71 on the periodic table is. Not 71, the element that has the mass of 71. You can also use the mass spectrometer to investigate molecules themselves. And so once again, turning things into cations because we're converting it, we're ionizing it, we're pulling an electron off. So you have the big peak is always going to be essentially the parent molecule. One loss of 1 electron isn't really going to change the mass of the substance. So 44 is really how much it weighs. But as you ionize it more, you could actually blow the molecule apart. And so you can see you could get, this is CO2, but you could get CO if we pull 1 oxygen off. If we pull the oxygen off, obviously not only is the CO left going to show, but the O is going to show. And then if we pull all of the oxygens off, we still have a C. So you can see that we wind up with peaks where you have the different masses. And so scientists use this information to try and predict what kind of molecule they're looking at. All right, so there's our introduction to